Hey, what's up, guys? My name's Paul. I'm gonna be behind the camera doing the narration. That guy up there, his name's Brendan. He's gonna be doing the illustrations. And this is our fork system call tutorial. Let's do this. Okay, let's say we have a process, our program, that contains a couple of variables, a is equal to 1 and b is equal to 2. We will represent a process with a circle. Now, how would we identify this process? All active processes are uniquely identified by a PID or process identifier. For simplicity of our video, let's assign this process with a PID of 5. In your own program, you can use the system call getPID to find the PID for your own processes. When we call the fork system call on this process, it creates a new process called the child, which is a duplicate of the calling process that is now referred to as the parent. Now, when we say that the child is a duplicate, what we mean is that fork makes two identical copies of address spaces, one for the child and the other for the parent. Both processes are an exact copy of each other, except for their process identifiers and a few other minute details which don't really concern us. After a successful call to fork, both processes will start their execution at the next statement following the fork call. Now, the PID of the calling process is not important here. What is important is the integer each process returns. If the process returns 0, we know we're in the child, else if the process returns anything other than 0, we know we're in the parent. Now at this point, both the parent process and the child process contain variables a is equal to 1 and b is equal to 2. After forking, it is unclear as to which process will run first, which is why we utilize the wait system call on the parent, to ensure that the child goes first. Using wait also ensures that the child terminates properly, preventing it from becoming a zombie. Now, we'll go into further details on this in a minute, so hang tight, guys, alright? Now, in our example, if we wanted to change our a and b to a is equal to 7 and b is equal to 8 temporarily, we would only do the changes to the child. After the variables are changed and used for whatever reason, we exit the child, resuming in the parent.
In the previous lecture, we have
Hello. Hey everybody, have you ever wondered where little computer processes come from? Little baby programs? Well, today we're going to find out. But first, some terminology. So you're a programmer, the things you create are programs, the things you write, the code you produce, those are programs. When you run a program, it becomes a process. It's important to keep straight the difference between programs and processes because you can have one program can produce many running processes that are just different versions of the same program. It's kind of like in an object-oriented programming language, how you can have one class and from that class you can create many objects of the same class. Kind of the same thing, it's very similar. But I digress. The question for today is how are little processes created? But everybody knows processes are created by the program launcher, by the command shell, in the terminal, right? But that's kind of unsatisfying. How does one process create another process? How do we make little baby processes? In Windows, you'd use the Create Process API. And it's shown here, it's basically you give it a bunch of information, you tell it what program you want to run, and you give it some properties, some attributes, and it just runs the process. There, I did it. I gave Windows-specific programming advice. Are you happy? Because it kind of hurt. It just hurt just a little. Don't expect this to happen very often. If you're on just about any other operating system, Linux, Mac OS, FreeBSD, you're going to use fork. And I know it's not immediately apparent why a function that creates processes is called fork, but it'll make sense in a minute, maybe. In any operating system that's based on Unix, processes all come from a single process. You start up the program and there's an initial process. It's usually called init. Sometimes you'll see it'll be called kernel task or something like that. But there's an initial process that creates all other processes. When you look in the process list to see all the running processes, these are all really clones. They're all clones off of that original process. And so when you call fork, you're just requesting a clone be made of your process. In this example, I call fork, and now instead of printing out one hello world, I get two. Because I've got two clones. I've created a new process, it's a clone, it's an exact copy of the original. Well, it's not quite identical. They actually have different process IDs. So a process ID is the number that the operating system uses to keep track of each process, and when I clone the process, the new process, the child process, actually does have a new process ID. And you can see that here, I've printed it out, and you see that they actually do have different process IDs. So you can look at all the processes that are running on your system using PS, using top, or some kind of graphical task manager, activity manager. Every operating system's tools are a little different, but every operating system has utilities that allow you to actually look at what's running on the system. The other thing I should point out is that all of these systems are going to show you a list of processes. We think of it as there's this list of processes, but even though they show you a list, it's more helpful often to think about this as a tree. It's like a big family tree of clones. Each process in this list has a parent, that's the process that cloned it, and each process can have multiple children. So when a process calls fork, it's creating a child process. The original caller is the parent, the new process is the child. As we've mentioned, they have new PIDs. Basically, each process then can call fork a lot of times, and you can create a lot of different processes. And I guess that creates family trees that kind of look like a fork, I guess. So maybe that's why it's called fork. But the point is Unix is really family friendly. It's all about relationships. It's all about these bonds we form with our process family. But clearly my example so far isn't very useful, and that's because both processes do the exact same thing, right? The problem with clones is that usually when you create a new process, you don't want that process to do the exact same thing as the original parent. You want it to do something else. You want to sort of create this child to have it do something useful while the parent is busy doing something else. And also from this example, it's not even clear that the child and the parent know which one's the child and the parent. So how do we do this? Well, for this, we check the return value of fork. Fork returns different things to the parent and to the child. To the child, it returns 0. To the parent, it returns the process ID of the child. And that may seem strange to you. Why return the process ID of the child to the parent? And why does the child just get 0? Well, the reasoning goes something like this. The child usually just needs to know it's the child. And so 0 is an easy thing that we can check. We can just say, hey, did fork return 0? Then I'm the child. The parent, on the other hand, has more responsibilities, as parents always do. And parents actually have to keep an eye on their children. So if I'm a parent process that's created a child process, I may need to wait for it. I may need to check on its status and see if it's still running. I may want to communicate with it and get some data back from it. And if it's just taking too long, I might just need to kill it. This video got a little dark all of a sudden. The point is processes are all about relationships. They're one big family with serious issues. But the point is that now I know who's the child and who's the parent. I can actually make the child do something different from the parent with a simple if statement. All I do is say, if fork returns 0, now I do something different. So I can, in this case, I can print out something different than hello world, and so you can now tell that the parent and the child are actually not the same process. They're doing different work. So now this is a whole lot more useful. So that's fantastic. We can now run something different in the child than we did in the parent. What else could we possibly need? A lot, really, unless you plan to have all the source code you might ever need to run in a process in that original process, then this is a little limited, right? Because any clone we make actually has to already have the code that we want to run. And that may not be very helpful all the time. That may not be what we want. And naturally, right about now, you're probably thinking, but really what I want to do is I want my process to create another process that's running someone else's program. I don't have the source code, it's a compiled binary, maybe it's Microsoft Office for all I care, and I just want to run it. How do I do that? But unfortunately, I'm going to have to make you wait. That's all the time I have for today. And we'll pick up this conversation next time when I teach you how to make your clones transform into something useful, something like, basically like another program.
This video covers the basic operations of fork and exec system calls in Linux that are used to create new processes and then run new programs. Running a new program on Linux involves two key steps. First, the currently running process is forked. Fork basically creates a new process, but is identical to the parent process that created it. Next, the currently running program in the child process is replaced with a different program, thereby having a different program start running. So for example, if the bash shell wants to run a new command, first it'll fork itself to create an identical copy of itself, but it'll be a completely different process with a different process ID and a completely different layout, but the virtual memory will be identical to the parent. Next, the child process will call exec or one of the family of exec system calls to replace the currently running program with a different one. For example, here let's say bash wants to run the ls command, then it'll replace itself with the ls program by calling exec. Note that here the program changes and the virtual memory layouts change, but the process ID does not change. Fork is a system call that is used to clone a running process. The clone process is a child of the parent. The parent and child are identical processes in the sense that they have exactly the same virtual memory layout, so they have exactly the same stack, so the sequence of method calls and parameters on the stack will be identical between the parent and child. Both the parent and child have exactly the same virtual memory, so pointers and other data structures that are there are preserved. Moreover, both the parent and child have exactly the same set of files, sockets, and other devices that were open before. So the parent and child could reading from the same set of associated with them. However, the clone process does differ a little bit from the parent in that it has a completely different process ID because it's a brand new process, and the return value of fork in the parent and child are different, and this is used to tell the difference in parent and child process, and this value can also be used to logically do different operations in the two processes. Let's do a deeper dive into how fork works. So assume that a program is already running in memory. Its process ID is 123. it has it is doing some input-output operations. That means it's reading data from a couple of different streams, for example. There could be more files or more sockets open at this time. And assume that we are going to start tracing the operations of the program just before the fork system call is made. So first the parent runs and it's going to print forking on its output. In the next line, it's going to call the fork system call. As part of calling the fork system call, remember that an identical copy is made. So there's a completely new process, which will be an identical copy of the parent with the same set of input-output streams open. They could both be potentially be reading from the same file, or they're set up to be able to read from the same streams and files. Keep in mind that the child's virtual memory layout is identical, so the stack, heap, etc. are also identically set up between the parent and child. But keep in mind these are completely different processes, so even though the virtual memory layout is the same, they are mapped to completely different physical memory locations by the operating system. Next, both parent and child will start running the line of code right after the fork system call, because keep in mind they're identical. Just like the parent call the fork system call and will go to the next line, the child will also start executing from the next line after the fork system call. So they are both going to print forked on the output as part of the cout statement there. Note that these outputs can appear in any order because of preemptive scheduling and context switching in Linux, so the order in which these outputs appear is not deterministic. Next, both parent and child will execute the next line of code, and they will print the PID values in each one of those processes. Note that here, the process IDs, the PID values printed will be different. The parent will print the process ID of the child that it created, but in the child process,